Hey everybody, welcome back to Chem 103 lecture. We're starting Chapter 9, Chemical Equation Calculations, otherwise known as stoichiometry. Before you start this chapter, make sure that you remember balanced equations and how we interpret them. I'll give you a little bit of a refresher. But also the mole concept, pretty much all of Chapter 8. Molar mass, molar volume, converting molecules or atoms to moles, all those things you need to remember. So if you're a little bit fuzzy on any of those topics, go back, refresh yourself, and then come back to Chapter 9. First, a refresher on interpreting chemical equations. Let's say we have a reaction where nitrogen monoxide gas and oxygen gas come together and make nitrogen dioxide gas. Needs a little bit of UV to help. In a balanced chemical equation, you have the same number of atoms of each element on the reactant side and the product side. The reactants are like the ingredients. You mix them together and you make a product. The coefficients that are in front of each compound, and remember, if there's no coefficient written, it's a 1. These coefficients can be interpreted as number of molecules, but it can also be interpreted as number of moles. So I can read this equation as 2 molecules of nitrogen monoxide to combine with 1 molecule of oxygen gas to produce 2 molecules of nitrogen dioxide. I could also say 200 molecules of nitrogen monoxide, 100 molecules of oxygen gas, 200 molecules of nitrogen dioxide. But the most helpful one is all the way down at the bottom. I can say 2 moles of nitrogen monoxide are combined with 1 mole of oxygen gas, and that makes 2 moles of nitrogen dioxide. This is the interpretation that we're going to be using throughout this lecture. The coefficients of a balanced chemical equation represent the moles of each species that are involved. When we have a balanced equation and we only have gases present, then they can also represent the volume of gas as long as we're at the same temperature and pressure. So what that means is I can say 2 moles, 1 mole, 2 moles, or at the same temperature and pressure, 2 liters, 1 liter, and 2 liters. That's only for gases. We'll revisit this when we're doing the different stoichiometry problem types. So tuck that in your back pocket, just keep it around. The reason why we can do these stoichiometry problems is because of the law of conservation of mass. Mass is neither created nor destroyed. So the mass that you start with of your reactants should be equal to the mass of your products. Now in the real world, there's loss. But it's not because matter is created or destroyed. It's just because maybe you don't get all your product out. Maybe the reaction is 100% efficient. All sorts of things. Error is one word to summarize all of those things. But we can do theoretical calculations to figure out, for example, how much product we'll make if we're starting with X amount of a reactant. To do those kinds of problems, we have to use something called a mole ratio, and this describes the relationship of the different compounds within the chemical equation. Remember that for a mole ratio to be valid, you have to use a balanced chemical equation. The mole ratios that we write can be used as unit factors. How do you write these mole ratios, I'm sure you're wondering? Well, all you have to do is write down the number of moles that you see within the chemical equation, and you're done. Right now, we're looking at an equation where we're making nitrogen monoxide by mixing nitrogen gas and oxygen gas. There's no coefficient out in front of these, so remember that means that there's a 1 here. And for the nitrogen monoxide, there's a 2. Let's say that I wanted to have the mole ratio for nitrogen gas and nitrogen monoxide. I look at the chemical equation. I see 1 mole of nitrogen gas. I see 2 moles of nitrogen monoxide. These are from the chemical equation, and it has to be balanced. With unit factors, they always come in pairs. We wrote 1. The second one is simply the reciprocal. You put the 2 moles of nitrogen monoxide on top, 1 mole of nitrogen gas on the bottom. Let's do another. This time, we'll look at nitrogen gas and oxygen gas. How many moles of nitrogen gas are in the balanced chemical equation? 1. Likewise, there's 1 mole of oxygen gas. There is 1 mole ratio. The second one, you just flip it. The third set of mole ratios that we can write is between oxygen gas and nitrogen monoxide. There's 1 mole of oxygen gas for every 2 moles of nitrogen monoxide. And we can write the reciprocal. We'll do more practice for writing these in class, but writing a mole ratio and choosing the correct mole ratio to complete your stoichiometry problem is key. It is the crux of all of these problems. So make sure that you can write mole ratios, and when we get to using them, you can choose the correct one. If chapter 2, where we talked about the metric system and we did conversions, if that was difficult, then you'll want to kind of revisit that, because that's the style of problem that we're going to be doing. These are pretty much fancy chemistry conversion problems. So here's a sample problem. How many moles of oxygen react with 2.25 moles of nitrogen? I always like to rephrase the question. I'm starting with 2.25 moles of nitrogen gas. And the question is about how many moles of oxygen gas react with it. So I need the mole ratios between nitrogen gas and oxygen gas. There are only two. We're looking at nitrogen gas. Remember, no coefficient means there's a 1. Oxygen gas in the chemical equation, 1 mole. That's 1 mole ratio between nitrogen gas and oxygen gas. Then you write the reciprocal. We have to use one of these to convert our moles of nitrogen to moles of oxygen. We're trying to get rid of moles of nitrogen, and currently we have that in the numerator. The unit factor that we choose has to have moles of nitrogen in the denominator so that we cancel it out, and we're left with oxygen gas. So this is a very simple problem that shows you how to use mole ratios. We started with the number of moles of nitrogen gas, and we used a mole ratio. I may also call it a mole-mole factor. It's the same thing. But we used a conversion to get from moles of nitrogen gas to how many moles of oxygen gas we need to react with it. So stoichiometry is the use of these relationships in a balanced chemical equation to carry out calculations involving the reactants and products of those equations. There are 3 types of stoichiometry problems that we're going to cover. There's mass to mass, mass to volume, and volume to volume. We'll go over each one. I'll give you a generic how to solve it, and then I'll go through a sample problem. We will do lots of practice in class. We take 2 weeks to cover this chapter because practice makes better. I'm not going to say perfect because ain't no such thing, but practice definitely makes better, and that's what we need to do. First problem type, mass to mass. You're going to be converting a given mass of a reactant or product to an unknown mass of reactant or product. So let's give you a little something to hold on to because it's kind of abstract. Let's say that we've got this equation here. And I told you in the problem that you're starting with 5 grams of A, and I want to know how many grams of C you can make. The steps that we're going to do for this are as follows. Starting with that 5 grams of A, we're going to use the molar mass of A to calculate the number of moles. You'll need to calculate the molar mass of each of your reactants or products that you're using in these calculations. Once you have moles of A, you need to use a mole ratio from the chemical equation that will get you from moles of A to moles of C. Last but not least, we need to get from moles of C to grams of C. You're going to put the molar mass of C at the top and 1 mole of C at the bottom. And that will get you to your number of grams of C. I'm going to try to use the same color scheme whenever we're going through these problems. In red, it's going to be the molar mass of the given. Green, the mole ratio. And this blue will be molar mass of your unknown. Let's put this to work and do a sample problem. What is the mass of mercury produced from the decomposition of 1.25 grams of orange mercury 2 oxide? Now, in this problem, it was written friendly enough to where we don't have to calculate a molar mass. So that's great. Here's what we know so far. I've got 1.25 grams of orange mercury 2 oxide. It's decomposing, and I need to figure out how many grams of mercury I'm going to produce. Our given information is on the left. Our unknown is on the right. We know the molar mass of the mercury 2 oxide. We can also figure out the molar mass of the mercury. Just look at the periodic table. Let's write out our plan. Starting with 1.25 grams of mercury 2 oxide, we first have to convert that to moles. And that's using the molar mass. Then we have to use a mole-mole ratio, or a mole ratio, mole-mole factor. There's so many different names for the same thing. That will get us to the number of moles of mercury that are produced. To get to grams of mercury, we use the molar mass of mercury. Now let's start filling in the numbers. That's our given information. We're going to do the same thing that we did on the last slide with our generic plan, but we're going to fill in the numbers. That will get us to moles. Then we need to have a mole-mole ratio. We need to have the unknown at the top, and we look at the chemical equation. There's 2 moles of mercury produced in the balanced chemical equation. And that comes from 2 moles of mercury 2 oxide. That's our mole ratio. Finally, we use the molar mass of mercury. Before you touch your calculator, make sure that you go through and do your unit analysis. Make sure all the units cancel, and you end up with the units that you desire at the end. You can follow along with your plan. The first step of the plan was to get to moles of mercury 2 oxide, and that's what happened. We cancel out the moles of mercury 2 oxide, and we have moles of mercury. We get rid of the moles of mercury, and we've got grams of mercury. Putting this into your calculator. 1.25 divided by that molar mass multiply by 2, divide by 2, which is the same thing as like multiplying by 1. But for completion's sake, we're going to go through and say each part, even if it feels a little bit silly, because it won't always be 2 to 2 or 1 to 1. So make sure you pay attention to that mole ratio. Then we multiply by the molar mass of mercury. When you do all that fun math, you end up with 1.16 grams of mercury. Don't forget units. I don't know that 1.16 is in grams unless you tell me. So please tell me. I need to know. The next problem type, mass to volume problems. With these problems, you've got a given mass of a reactant or product, and you're asked to figure out the volume of a reactant or product. That reactant or product will always be a gas because that's the only thing that we do volume with. Let's give an example. Say that we have our same little equation, but this time C is a gas. If we're starting with 5 grams of A, we want to figure out how many liters of C we make. Could be liters, could be milliliters. Pay attention. As long as it's some kind of a volume, then we're looking at a mass to volume problem. In class, we'll focus on identifying the problem type and then doing the practice. It's a little bit more difficult to do that when you have the title and you know what type of problem it is in the pre-recorded lecture. So that's one reason to come to class, because you'll get more, real practice at identifying the problem type and doing the actual calculations. Okay, enough about that. Let's give you the generic, how do I work through this? There's our given information. We have 5 grams of A. The first part is always the same. We have to get from grams to moles. If we're not starting in moles, we have to get there. Then we have to use that mole ratio. In our equation, it's 1 to 1, but it could be anything, whatever that mole ratio is. The last step looks a little bit different, and I should use a different color because it is something different. I'll always take an excuse to use a bunch of different colors. Hopefully you can see the difference between that blue and this purple. In the purple, we have brought back molar volume. Remember, 1 mole of gas has a volume of 22.4 liters at STP. That's what we'll be using for these problems. So you'll see a mass of a reactant or product. You need to figure out the volume of a reactant or product, and you'll see something about it being at STP. Use molar volume to get to liters. That's kind of abstract. I always like to show you an actual problem. So let's do that. How many liters of hydrogen are produced from the reaction of 0.165 grams of aluminum metal with dilute hydrochloric acid at STP? This is a little bit of a throwback question, but you can look at this equation and think about what type of reaction it is, because you will have a final and you'll need to do that for the final. This is a single replacement. It's an aqueous acid replacement because we're taking a metal that is reactive and mixing it with an acid. But anyway, we need to take the aluminum, convert it to moles, and figure out how much of a gas we're making. So this is a mass to volume question. What do we need for this? Well, we're definitely going to need a molar mass here for the aluminum, but that's not a big deal. All you have to do is look at the periodic table. So let's write out the plan before we start putting in numbers. We've got grams of aluminum. We've got to get some moles of aluminum. We need that molar mass. We use the balanced chemical equation to write a mole ratio that tells us how much hydrogen gas we produce. Then we use molar volume because we can take the number of moles of hydrogen gas and convert to a volume because the reaction is occurring at STP. Time to fill in some numbers. If you can't tell, I actually really like stoichiometry, which I know, you're like, well, duh, you're supposed to like it. Well, it can be fun. You just have to make it fun. All the colors, and I feel accomplished. First unit factor. We're looking at the molar mass of aluminum. Then we need a mole ratio. There are 2 mole ratios that we can write here. I advise that you circle or highlight or underline the 2 compounds that you need to write the mole ratio for, just so that you focus on those and nothing else. There's 1 mole ratio. There's the other. We need to use the one that's going to get rid of aluminum and leave us with hydrogen gas. So that's the one we're going to use. Just wanted to show you how you can kind of write out the mole ratios and then choose the right one versus just writing it all out in one long string and not writing out both of your options. Whichever way you're comfortable with, that's what you do. Then we have to put in our conversion with molar volume. Make sure that your units line up with what you need. Grams of aluminum cancel. We're left with moles. Moles of aluminum cancel. Left with moles of hydrogen gas. Moles of hydrogen cancel. We're left with liters. To put all of this into your calculator, Parentheses are your friends. There you go. And when you type all of that in, that's what you should get at the end. Now make sure that for these questions where you're dealing with volume, that you pay attention to the units. Now in this question, we had liters, but you could see milliliters, in which case you would have to add on another unit factor to convert liters to milliliters. We'll do some practice with that in class. We can also do the reverse. Volume, you start with, and figure out how many grams. So how many grams of sodium chlorate are needed to produce 9.21 liters of oxygen gas at STP? We're pretty much going to do the same type of process, just in reverse. Always rephrase the question. So let's write out the plan for this one. We're starting with a volume of oxygen gas in liters. We're going to use molar volume to go from that to moles of oxygen. Then comes the mole ratio. And we get to moles of sodium chlorate. Then the molar mass of sodium chlorate will get us to grams. Let's write out the mole ratios that we have from this chemical equation. We're only concerned with sodium chlorate and oxygen gas. So for our mole ratio options, we've got 2 moles of sodium chlorate over 3 moles of oxygen gas, or we can use the reciprocal. We've got those written out. We can write out all the numbers and choose which one makes sense as we're going through. Starting with the 9.21 liters of oxygen gas. I always pre-make my bridges. First, we're doing molar volume. This time, we're trying to get from liters to moles. So we put moles on the top and liters on the bottom. If it's a volume to mass problem, and you're starting with using the molar volume as a unit factor, 1 mole in the top, 22.4 liters in the bottom. Then we have our mole ratio. We're trying to get to grams of sodium chlorate. So that's what we need. That should go in the top. The molar mass of sodium chlorate, I'll write it here. So we fill that in. Now, I'm sure you've noticed that I write out all the units every time. And not just the units like moles or liters, but also which compound. There's a reason for that. That reason is unit analysis or dimensional analysis. Make sure that the units you end up with match what you're trying to get to. The only way that you can do that properly is to write out all of your units every time. It's a little bit tedious. It takes a little bit longer, but it will save you points in the end. So do it. Write out the units. Get used to it. When you show your work, at least for me, it shows me what you know, and I can give you some partial credit. If you don't, and you just write down an answer, or you write down a bunch of numbers and they don't have any units or anything, I can't see what you know, I can't see what you're doing, and I can't tell you where you went wrong. So do us both a favor. Write out your units. Make sure that your work is neat and legible. It will save us both a lot of time and a lot of headache. Everyone gets a better grade when I'm happy. That's not necessarily true, but Anyway, I'll get off of my soapbox. Please write units. That's all I'm trying to get you to do. We get to moles of oxygen gas, moles of sodium chlorate, grams of sodium chlorate. Put it into your calculator. When you put it in like that, you should get 29.2 grams of sodium chlorate. And I really do recommend that you try putting it into your calculator and make sure that you get the same answer. One, never hurts to double check, right? Sometimes people make mistakes. If you see one, let me know. I want to know so I can fix it. But also, and most importantly, practice. Practice putting these equations into your calculator so that you know when you need to use parentheses and when you don't, because each calculator is a little bit different. So we're going to take a little bit of a detour. We're going to cover volume-to-volume problems, but we've got to talk a little bit about Gay-Lussac. We're going to talk more about him when we get to chapter 10, when we do gas laws, but we're going to talk about it a little bit now. He discovered that the volumes of gases under similar conditions, meaning the same temperature and pressure, combine in whole number ratios, and that's called the law of combining volumes. So similar conditions equals same temperature, which is T, and pressure, which is P. So consider this reaction. Let's say that we've got hydrogen gas, chlorine gas, and we're making some HCl. That's also a gas. If I take 10 milliliters of each reactant, I'm going to produce 20 milliliters of product. We already know that from the very beginning when we talked about with gases, you can also use volume when it's at the same temperature and pressure, not just moles. So that's not groundbreaking. But what you notice is that the ratio of the volumes, 1 to 1 to 2, they're small whole numbers. The whole number ratio is the same as the mole ratio in the balanced equation. So that's why we can use volume for gases when they're at the same temperature and pressure. That's also why volume to volume problems are the easiest. Save the best for last. You're starting with the given volume of a gas, and you're figuring out an unknown volume of another gas. There's only one step here. So let's say that we're combining two gases to create some other gas. You take your volume, so your number of liters of A. Let's give it a number. You know I don't like abstract things. Let's say you're starting with 3 liters of A. Just an example. All you need to do is write out the volume, which is pretty much like the mole ratio, but it's the volume ratio. This is the easiest problem type. There's only one unit factor. You use a volume ratio, which is pretty much the mole ratio, only instead of moles you say liters. Let's try one. How many liters of oxygen react with 37.5 liters of sulfur dioxide in the production of sulfur trioxide gas? Rewrite the question. This is our question. We're going to need a ratio between the sulfur dioxide and the oxygen. We'll use purple. If you haven't noticed, you're also using your Chapter 6 skills of being able to read the problem and identify the compounds based on the names. So if reading this problem you couldn't identify sulfur dioxide or sulfur trioxide, revisit Chapter 6. Anyhow, let's write some volume ratios. I see a 2 in front of the sulfur dioxide. I'm going to write that as 2 liters. I don't see anything in front of the oxygen gas, so that means a 1. Then you write the reciprocal. So it's going to be one or the other. We're trying to get from sulfur dioxide to oxygen. Sulfur dioxide is in the numerator. We need it to be in the denominator of our ratio. When you're putting this into your calculator, what you're doing is taking 37.5 and dividing it by 2. With sig figs, you get 18.8 liters of O2. Remember, these two cancel. You're left with liters of oxygen gas. Don't forget your units. And also watch these problems. Right now we see liters, but you could also see milliliters or something else. So make sure you answer the actual question. Liters, milliliters, deciliters. Make sure you really read. So we've built up all the stoichiometry problem types. Now we're going to add a concept on top of that. It's the limiting reactant concept. You might be hungry while you're watching this video, and if you are, I suggest you pause and make a grilled cheese, because we're about to talk about a grilled cheese. And there's nothing like grilled cheese with some tomato soup. If you have to buy the Campbell stuff, fine. Go buy you a can of soup. But if you can make it yourself, it is so much better. Anyway, let's say you're making grilled cheese sandwiches. To make the most basic grilled cheese sandwich, you need 2 pieces of bread, 2 pieces of cheese. If you don't have 2 pieces of cheese at least, you do not have a sandwich. You have a sadwich, okay? Don't have a sadwich. Put 2 pieces of cheese on there. If we wrote that as an equation, we'd have 2 cheese plus 2 bread gives you 1 sandwich. Let's say you're looking around the kitchen. You look in the fridge. You've got 10 slices of cheese. And you're like, oh yes, this is going to be great. Then you find the bread. You've got 2 slices of bread. You've got a lot of cheese, not a whole lot of bread. So hopefully you don't have more than one person to feed in this situation, because all you can do is make 1 sandwich. Even though you have a lot of cheese, you only have 2 slices of bread. Your cheese is in excess. You've got much more of it than you can use to make 1 sandwich. But 2 slices of bread limits how many sandwiches you can make. And in this reaction, it would be the limiting reactant. Got a ton of cheese. We can make far more than just 1 sandwich with the number of slices of cheese we have. But we've only got enough bread to make 1 sandwich. Now, in the real world situation, you could take them 2 pieces of bread and put, 10 pieces of cheese is a little bit much. But you could have as much cheese as you want. You can do what you want. Grilled cheese is very customizable. But I digress. Limiting reactant. It's the one that shows you how much of your product you can actually make. And in chemistry, the limiting reactant is used up before all the other reactants. Everything else is present in excess. We can take this concept and put it on top of the stoichiometry problems that we've been doing. So let's start slow. We're going to determine the limiting reactant in this problem. It's just going to be moles, okay? We're not doing any mass to mass or anything like that yet. If you heat 2.5 moles of iron and 3 moles of sulfur, how many moles of iron 2 sulfide are formed? We've got 2.50 moles of iron, 3 moles of sulfur. We don't know how many moles of product we're going to make. The hallmark of a limiting reagent or reactant problem, reagent, reactant, same thing, is that you get the information for 2 of your reactants. That means what we're really doing is 2 mini problems within the same question. I'll do the first one in blue. The first question we're asking is, if I had 2.5 moles of iron, how many moles of sulfur could I make? Well, I need a mole ratio. What I need to find is the number of moles of iron 2 sulfide. I look at that in my chemical equation. Then I look at the number of moles of iron, put that in the bottom. If I had 2.5 moles of iron and unlimited sulfur, I could make 2.5 moles of iron 2 sulfide. The second mini problem that we have is taking those 3 moles of sulfur and figuring out how many moles of iron 2 sulfide we can make. We're going to go through the same process. What I need to figure out is how much iron 2 sulfide. So the number of moles of that for my chemical equation go in the top of the mole ratio. What I'm given information about is the sulfur. I go to the chemical equation. I see 1 mole. So if I had 3 moles of sulfur and unlimited iron, I would make 3 moles of iron sulfide, iron 2 sulfide. But we can't make both of these. We've only got 2.5 moles of iron, 3 moles of sulfur. So whichever one makes the smallest amount of product is the limiting reagent. And that tells you how much you're going to make. In this case, the iron makes the least amount of product. So that means it is rate limiting. Or not rate limiting. Ooh, that's a whole different topic. It is the limiting reactant. The amount that we would make of our product is 2.5 moles of iron 2 sulfide. So we have 3 different types of stoichiometry problems, and we've got the limiting reactant concept. In words, I've got how you can solve this problem. But you know me. I like to do an example. So this is for all the people who like to have something to write in their notebook. You can copy it down, you can print it out. But I think going through the process will help much, much more. We've got molten iron being formed. We need to figure out how much of it is formed when we react 25 grams of iron 2 oxide and 25 grams of aluminum. We've got starting amounts for 2 reactants. So that tells you it's a limiting reactant problem. We've got 2 mini problems to do. The first one is to take 25 grams of iron 2 oxide and figure out how much molten iron we make. The second one is to take 25 grams of aluminum and figure out how many grams of iron we make. Then you choose the limiting reactant, and that tells you how much product you'll make. Let's get started. For the first one, we're starting with the grams of iron 2 oxide. We're going from grams to moles. And that requires the molar mass. We get to moles of iron using a mole ratio. We get to grams of iron using the molar mass of iron. The molar mass of iron 2 oxide is 71.845 grams per mole. And if you're wondering where I'm getting these molar masses, go back to chapter 8, because we talked about how to calculate molar mass. And if that's a question you have, then you need to go back and revisit chapter 8 with the mole concept. Now that we've got all the information we need to solve this one, let's start putting in some numbers. Starting with the molar mass, we need to get to moles of iron 2 oxide. Then we need a mole ratio. What we're trying to figure out is the moles of molten iron. So you look at the chemical equation, you write how many moles you see. What we're given information about in the problem is iron 2 oxide. You look at the chemical equation for that. Write it in the bottom. Hopefully me doing multiple different ways isn't confusing, but instead you find something that makes the most sense to you. So feel free to let me know if multiple ways is confusing or helpful. We use the molar mass of iron. There we go. We make 19.4 grams of molten iron. But we're not done. We still have to figure out how much we would make if we had 25 grams of aluminum that we were starting with. It's the same kind of deal. I will add up with our other molar masses the molar mass of aluminum. We're following the same exact plan, but this time it's aluminum. Look at your chemical equation. We're trying to figure out the number of moles of iron we make. That should go in the top. What we're figuring that out with is the moles of aluminum. That was our given. Write that down in the bottom. That last unit factor should be the same for both of these problems because we're taking the moles of iron and converting it to grams of iron. Now we decide which one makes the least amount of product. That means that to answer our question, we would make 19.4 grams of iron. And just because we can, we'll say that iron 2 oxide is limiting. Here's a limiting reactant problem that involves gases. Again, when we're doing gases, it's pretty straightforward. How many liters of nitrogen dioxide gas can be produced from 5 liters of nitrogen monoxide and 5 liters of oxygen gas? Again, we have information for 2 reactants. Need to figure out how much of the product we're going to make. first question that we answer, if I have 5 liters of nitrogen monoxide, how many liters of the product do I make? Second question, if I start with 5 liters of oxygen, how many liters of nitrogen dioxide do I make? We'll start with the first one. Look at the chemical equation. We're trying to figure out how much of the nitrogen dioxide we make. So the number of liters of that from the chemical equation should go on the top. The number of liters of the reactant, NO, should go on the bottom. That's the first part. Second part, we're doing the same thing, only with oxygen. Oxygen doesn't have a coefficient in front of it, so we just say that it's 1. Coefficient in front of the nitrogen dioxide is 2. Then you figure out which one of these makes the least amount of product. So it turns out that we'll make 5 liters of product if we mix these 2 gases in these volumes. This is probably the easiest kind of limiting reactant question that you'll get in terms of combining that with stoichiometry. Now, I alluded at the beginning when I was talking about the law of conservation of mass that we don't always make 100% of what we're supposed to make. And that's because maybe you didn't scrape all of one thing out when you were, getting it out of one reaction vessel to put into another. There are so many different reasons why. You could have tripped and dropped some. It happens. So when you perform a laboratory experiment, the amount of product that you actually collect is called the actual yield. That's real world stuff. The amount of product that you calculate from a limiting reactant problem is a theoretical yield. These are the stoichiometry problems we've been doing. The percent yield tells you the amount of actual yield compared to theoretical. And this is the equation. You've got the ratio of the actual yield over the theoretical times 100%. The actual yield will always be told to you because it's experimental. The theoretical yield, you may be told, but you may also have to do some kind of a stoichiometry problem to figure out the theoretical yield and then calculate the percent yield. For now, we're just going to do the simple problem type. Suppose you perform a reaction, you obtain 0.875 grams of copper to carbonate, and the theoretical yield is 0.988 grams. You need to calculate the percent yield. You have to be able to determine which is actual and which is theoretical. Then you put it into your equation. Actual yield goes on top. Theoretical yield on the bottom. Multiply by 100%. And there's your answer. Now again, this is the simplest type of percent yield problem. You're told the actual, you're told the theoretical. You divide, multiply by 100, you're done. But you may have to calculate the theoretical using one of those stoichiometry problem types. We'll do some of those in class so you get practice doing that as well. Thanks for watching. Make sure that you tune into the live lecture, especially for these chapters where we're doing a lot of math. You know that I like to do practice, 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 and give you feedback. So come to class, we'll do practice problems together, and I'll always give you details regarding assignments and exams. You get the most information when you come to class. I give you all the keys to the kingdom so you can do really well on your exams and your homework. Until then, be safe.